We are going to talk about polarity. So polarity is a very large property of molecules. It determines a lot of things that they can do and how they react and how they interact when they're on their own. What you guys are going to need is you're going to need a notebook. You're going to need a writing implement. You won't need a calculator or anything else like this. Just those two things. So once you have those ready, let's go. All right, so first thing we should probably do is starting off by talking about what is polarity. Polarity is based on something called a dipole. A dipole is basically a separation of charge. Right, so by separation, what I mean is that one side of the object has a positive charge, the other side of the object has a negative charge. Right, so for example, if we take an object that you guys are all familiar with, right, so we're just going to take a battery. Right, this side right here, this part of the battery is positively charged. This side of the battery is negatively charged. This is a dipole. It's a separation. One side's plus, the other side is minus. We can apply this concept to a molecule. Now, normally the way that I would go about doing this is we'd look at shapes and electronegativity charts, right? Because electronegativity is one of the properties that determines polarity. You've seen this word before, but it's been a few months. This was actually the last thing we covered before we started this distance learning thing, so it's been a while. Normally, this is what I would go into immediately after that unit, but things are what they are. Electronegativity is basically pull for electrons. Right, so the higher the electronegativity an element has, the more pull it has for other electrons. Fluorine wants other electrons by a large amount, so it has a very large electronegativity. Noble gases don't have an electronegativity because they've already got a filled valence shell. They don't need any more. Right, so this is normally what we do. We'd combine this concept of electronegativity, and I'd spend about a week or two going over how to determine molecular shape in 3 dimensions. But that's something that I really can't do very well with you guys unless you have access to model kits, so we're just not going to do that. I'll give you guys the shortcut method of this. Molecules work the same way that these objects do. Right, so a molecule is polar if one side of the molecule has a positive charge and the other side of the molecule has a negative charge. Right, so as an example, let's take, what would be a good one? Let's take, we'll do hydrochloric acid, so HCl. Now, if we looked at the electronegativities, chlorine has a much higher electronegativity than hydrogen does. That means that chlorine wants to be negatively charged, and the hydrogen is going to be positively charged. One side is plus, the hydrogen side. The chlorine side is minus. That makes it polar. Now, one thing I will point out is that it is possible for a molecule to consist of nothing but polar bonds or dipoles, but overall have them be arranged in a way that cancels themselves out. This is one of those things that you would typically need a model kit to determine. I'm going to give you a set of rules to do this with. Right? But it is possible for a molecule to have lots of these type of bonds in it, but for them to be arranged in such a way where the molecule overall isn't polar. And the key thing here, the key reason why this happens is because we're talking about sides, right? So one side positive, one side negative. If the center is positive and all the things outside of it are negative, that doesn't count, right? So left and right, top or bottom, not in and out. Right, so here are the rules to determine if something is polar. First rule, if every atom in the molecule is exactly the same, it's nonpolar, right? Because if we're talking about the same atoms, again, polarity is based on pull for electrons. If I have, for example, 2 oxygen atoms in a molecule, right? So the O2 molecule. Each of these oxygens wants electrons the exact same amount. If they want them the exact same amount, there's no pull one way or the other, so the molecule isn't polar. If you have different elements in the molecule, which is going to be the case about 90% of the time, look at the central atom. Or, in some cases, central atoms if you have larger molecules. All right, so if we look at the center atom, we're going to look for two things. If the center atom has a lone pair on it, it's a polar molecule. If the center atom does not have a lone pair on it, but it has different things attached to it, it's polar. Right, so to explain these couple of things right here, if we actually look at, so center atom has a lone pair. That's actually relatively straightforward. I'll look at ammonia. So ammonia is NH3 with a pair on the nitrogen. The central atom of this molecule is the nitrogen. The nitrogen has a pair of dots, right? That pair of dots makes it polar, because what that pair of dots does is, if we're talking about 3 dimensions, it breaks the symmetry of the molecule. Right, so this lone pair makes it polar. Now, multiple types of atoms. Again, if we actually look at, I don't want to do anything that's already on your sheet that I'm going to give you. But we'll look at carbon, for example. So we're going to start off with CH4. Right, so CH4, all 4 of these things attached to the center atom are the same. They're all hydrogens. Right, so all hydrogens, non-polar. Now, if I change out one of those hydrogens for something, so let's say that I change out one of those for a sulfur. Now I have sulfur and hydrogen on the outside attached to that center atom. Because there are different atoms attached, this is polar. This molecule we can break the symmetry of. Right, so that's what you're looking for. And what we're going to do is we're going to go over a few examples of this. Right, so for the first few, we're going to go over them pretty much as a group. For the last 2, I'll give you an opportunity to work on them, and then we'll go over them. Right, so we have hydrofluoric acid. The Lewis structure for hydrofluoric acid is HF right up here. So what we're looking for is we're looking to see if this molecule is polar. Well, we only have a 2-atom molecule, so there's no center. But if we look at it, are the 2 atoms the same? No. Because these 2 atoms are not the same, the molecule is polar. One atom is going to have more pull than another. And the diagram I'm going to bring up is what's called an electron density diagram. This actually shows the charge distribution of the molecule. Right, so this blue part right here means that this is positively charged. The red part is negatively charged. So our hydrogen and our fluorine. Notice how one side of this molecule is positive, the other side is negative. Right, so that's how this diagram kind of works. You'll see a few more of these as we go through, but this is just kind of a useful tool to show you what it actually really does look like. Right, fluorine, because it has a very high electronegativity, wants electrons badly. So it's going to take as many as it can get. Our next molecule is ozone. Ozone is O3. So here's our Lewis structure for ozone. When we're doing this, we apply those 2 rules I gave you in order. Right, because the first thing you might look at is go, oh, lone pair must be polar. Apply those 2 rules I gave you in order. First rule, is everything in this molecule the same? Yes, everything in this molecule is an oxygen atom. Because they're all the same atom, The molecule is nonpolar because there's no net pull. All oxygens are pulling equally. Right? It's like a tug of war where both sides have the same strength. Now, I don't actually have a electron density diagram for ozone. I couldn't find one. But if you saw one, what you would see is that instead of being red or blue, the entire molecule would basically be some shade of green, green being neutrally charged. Right? So these are the first two. The next two can be a little bit trickier, so we're going to look next off at water. Water is a very common compound. Now, you guys probably know water from middle school. You've gone over the fact that water is a polar molecule. Now we're going to explain why. Right, so here's our water molecule. I'm going to apply my first rule. Is every atom in this molecule the same? No, I have an oxygen and two hydrogens. They are not the same. Now I'm going to apply my second rule. So second rule, does the center oxygen have a lone pair on it? Yes, in fact, it actually has two lone pairs on it. Because it has two lone pairs on it, it's polar. Right now, a lot of people would look at it and go, oh, well, it has two H's attached, so it shouldn't be. But in this case, the lone pairs make it polar, right? So these lone pairs are going to be overall negatively charged. The hydrogens are going to be positively charged, right? So what we wind up having with water is we have a negative charge on top and a positive charge on bottom where the two hydrogens are. Again, one side plus, one side minus. The next one I'm just going to do quickly is carbon dioxide, CO2. Here is the Lewis structure for CO2. Again, we're going to apply our rules. First rule, is everything in this molecule the same? No, we have two oxygens and a carbon. Second rule, I'm going to look at my center carbon. Is there a lone pair on this center carbon? No. Now, is everything attached to this carbon the same element? I ignore double and triple bonds. I just look at what elements are attached. So attached to this carbon is an oxygen and another oxygen. Because both things attached are oxygens, the molecule is nonpolar. Now, the key thing to keep in mind here is that both carbon-oxygen bonds themselves are dipoles, right? So what happens is that the oxygen here is negative, the oxygen here is negative, the carbon is positive, right? So these bonds are actually dipoles, but they are arranged in such a way where we have a positive center and negative outsides. Again, positive center, negative outsides are nonpolar. It has to be one side plus, other side minus. Right, so here's our molecule, and again, we notice we have a bunch of greenish red on left, greenish red on the right, and in the center we have a bunch of blue indicating our positive carbon. Right, so this is when it gets a little bit tricky. So just follow the rules and you will be fine. Right, so let's try a couple of these. Let's have you try a couple of these. So the two I want you to try are carbon tetrachloride and formaldehyde. Right, so pause the video, attempt to determine if these are polar, and if they are or are not, tell me why. And then once you have that, please pick the video back up. Okay, so we're going to start off with CCl4. Again, if we follow our rules, is everything in this molecule the same? No. Now we go to our second rule. Second rule, does this carbon have lone pairs? No. Is everything are there different types of atoms attached to the center atom? No. Everything attached to this center atom is a chlorine. Because everything attached is the same, the molecule is non-polar. It's all pulling out from the center. This works just the same way carbon dioxide did. We have a positive center, which is this little bit of blue right in here, and we have negatively charged outsides, which is all of this red. Right, so positive center, negatively charged outsides in all possible directions. So this molecule is nonpolar because, again, I can't say top positive or bottom positive and have them switch off. Formaldehyde will follow the same rules. Different atoms attached, so we don't have rule number 1. Rule number 2, carbon doesn't have a lone pair, so we can ignore that. Then we look at this. Is everything attached to this carbon the same element? I have O, I have H, I have H. Because they are different elements, the molecule will be polar. Right in our diagram, again, the oxygen side is going to be our negative side. The hydrogen side will be our positive side. Oxygen is negative because oxygen wants electrons. It's only 2 away from a filled valence shell, so it wants more. Right, so this is determining polarity. For your assignment, I'm going to have you take the worksheet that you had due this week, and you're going to, on it, tell me whether or not each of those things is polar or nonpolar, and tell me why. Right, so which rule does it follow, which rules does it break? That's your assignment for this week. Next week, we're going to go over something called intermolecular forces, which is how all of this polarity winds up playing out when we talk about properties of molecules. Again, if you have any questions, feel free to send them to me in email. Otherwise, good luck on this.